Perfect. So, in terms of what we should be doing for our study time, to become a bit more productive. Oh, yep, went a bit blurry. In terms of being a bit more productive, the first thing I'm going to suggest to you is something called time blocking. Is that something you've done before?
No.
No. Okay. So all it involves, I've made some videos on online as well. All it involves is you basically over this next 2 weeks. So before term, let's think short term before we think long term. Short term, you've got 2 weeks before term starts, right? A bit under now.
My school actually comes back on the 30th, so I have 1 week.
1 week. Okay, great. Better. So very short term.
Yeah.
What I want you to do first of all is write down a list of absolutely everything you have to do. You don't have to write it out now, but as a first thing, you're going to write out a list of everything. So maybe just list out 3 things to start. What are 3 things that are super high priority on your mind that you have to get done before term?
I have a chem assignment,
Chem assignment?
like chemistry or at school in general.
Anything. This is
I have
beyond just chem.
I have some Japanese homework, some maths homework, and some chem homework.
Okay, cool. And that has to be done.
Mhm.
So we have the tasks defined. I want you to start thinking about studying in terms of tasks rather than time spent. That's the moment where you start clicking into productivity rather than just sitting there and wasting your time away because you feel like you should be spending 2 hours per day on this and you feel like, no, think tasks. You have tasks defined. You've got, I think you said 3 of them there, right? I want you to now allocate how much time does each of those tasks take? So for your chem assignment, how long do you need? Roughly guess.
Ooh, I don't even know. 4 hours, maybe a little bit
Oh,
more.
okay, fine. Next thing, was it Jap homework? How much for that?
Lab homework, closer on 3,
3 hours. And last task?
5.
5. Okay, all up 12. If you need, do you have anything else in your mind? There's a few other things maybe. Or is that
Yeah,
it?
a couple of small things, but nothing major.
A couple of small things. Say this is like half of your tasks that you have to get done before school comes back. You've got 9 days. Let's say you're going to spend 5 days on these tasks. It breaks down when you think about it. If you're finishing these 3 tasks in the next 5 days, that's 2.2 hours basically per day. Is that about what you expected to spend for these tasks?
Yeah, it's less.
Yeah, it's a bit
Yeah.
less, right? When you put it that way and you actually break down the tasks you need to do, how much you think you need to study to get these things done, your time shrinks all of a sudden because you're no longer
Yeah.
spending empty time just sitting there doing nothing. So that's the first thing I'm going to get you to do. Write down that full list for the next week after we finish today.
Mhm.
Define the time it takes for each of those tasks. And then plug these into your calendar for the next 9 days so that it fits within the amount that you're meant to be studying per day, which is going to be about 2 to 3 hours from the sounds of it. And that's very reasonable.
Wow.
Cool.
Yeah.
So that's my first study hack and probably the one that's benefited me the most over the last 3 years. But if you work on that, you get very good at understanding. I cannot emphasize enough. Study is not about time spent, it's about tasks completed. So the more tasks you can get done and clock them over each day, the better you'll get at just getting volume out. Okay. Any questions on that?
No, that sounds awesome.
Okay, try that this week and let me know how you go with it. But in the meantime, it seems like Benji is not responsive. I'll give him one more call. See how we go.
The person you have called is not available.
That's all right. All good. Just you and me then. You had a private session.
Awesome.
So you have the notes, right?
Yes, I didn't print them out, but I have them digitally.
That's fine. We're just gonna, the way the session's gonna work is we're gonna work on those notes, essentially go through them from start to finish. I've sent you only the first third though of all the notes. We're gonna get through most of it today. So it's gonna be fast paced.
Mm.
The policy is fast. We're covering fast so that you can get awareness first. You're not meant to understand everything today. So don't feel overwhelmed when at the end of it, you're like, oh my God, we've been through so much content. How am I going to hold this? No, don't worry. It's fine. It's going to feel just like a brain dump for a solid period of time. What is essential though, is that you ask questions as soon as you become unhinged. because I can't know what you're thinking. As soon as you become lost and you lose my train of thought, stop me because I'll go back and repeat what I said. Okay. The other thing we need to set up is a little doc. So I'm going to add you to this Google Doc now. I'll also add Benji in. I don't have his email here, but I'll add yours. I believe I have it. No, I don't. It's on Gmail, so I have to get it from here. This one? Oh no, it's probably stopped sharing. Okay, it should have sent now.
Yep,
Let me know if you get that.
got it.
Okay, perfect. Admin as well. Okay, so you'll see in that doc, there's a big table once you open it.
Mhm.
And there's a reason why we have that table. I use it with every student. Benji. Okay. There we go. All right. So you'll see that the table has two big headings. I usually just keep it as questions and solutions, but misunderstandings is also relevant as well.
Mhm.
What this table is, I want you to think of it as your personal log of all of your shortcomings in chemistry. Whenever you mess up, whenever you don't understand something, it goes into this table. Now, the way it's going to work in class is we're going to have our class table. And what I'm going to get you to do after each class or when you're free time, ideally after the class, is copy what we put into this table into your own document. So you can make a copy of this for yourself, and then you add your own personal mistakes and questions into there. But the way it works, if you lose all the marks on a question, if you lose 3 marks on a question, if you lose half a mark on a question, it goes into this doc. Okay. So for example, if last term you got asked the question, what is Le Chatelier's principle? And you messed it up by saying, oh, I don't know, maybe it's collision theory and collisions, then you have to write in this table, Le Chatelier's principle, what is it? And you write out a model solution for yourself. So you've figured out what you didn't know and you've corrected yourself. If you do this for everything that you don't know in chemistry at one point, and you go question, misunderstanding, solve it. Question, misunderstanding, solve it. You've got an entire table of everything in chemistry that you ever didn't know at one point. And guess what that does?
Guess?
Yes, go for it. How does that help you? How does that help you?
It reforms the pathways in my brain relating to the question. So I've made the mistake, but now I've got the supplied answer and I can go and learn from it every time I make the mistake.
Exactly. And it's all in one place, right? So when you revise, you don't have to go open your notes and read through the whole thing. No. Question solution table, every single mistake you've made, just study this table. And you'll eventually find what happens is because you've got this table anyway, and you've kind of hit yourself on the wrist for making a mistake, your brain has as you said, the brain pathways become more powerful. Have you ever thought about your brain's memory of painful or harmful responses to yourself and how that works?
It's much more, you remember it much better.
Right. Yeah. So when was the last time you injured yourself or caused yourself some sort of pain?
I stubbed my toe this morning.
How'd
Really.
that happen? How'd that happen?
I'm clumsy.
But what was the sequence of events beforehand?
Oh, okay. It was just over there.
Yeah.
I was walking out of my room and I stubbed my toe on my bed frame.
Yeah. So your brain said, no, that's bad.
Mm.
Connection it forms is stronger because you've given yourself pain. So this table is giving your brain pain signals. No, this is bad. You lost the mark. You don't understand. Slap on the wrist. So you'll remember it stronger if you're going to log it straight away, especially with the solution. So your brain remembers not only the sequence of events beforehand, But the solution, it's going to remember next time I walk around that hallway, I don't walk into the wall. You tell yourself to do that, right? So you need to give yourself the identification of the problem and then the solution. And that whole sequence will stick so much stronger once you start doing this. If you break this down, it's essentially just ugly flashcards, though. So you can make these into flashcards if you want to, because you're going to have the question on one side, solution on the other. You can make them into flashcards. Just fold a piece of paper over if you print it out. But this is what we're going to work off for whenever I need to type up things for you. Otherwise, I'll be screen sharing. Any questions before we get started? Because I'm very excited.
That's everything, I think.
Okay, awesome. Okay, module 6. Have you read into any of module 6 yet? It's okay if you haven't.
I think I read through those notes. I didn't get all the way through, and I didn't do it very in depth.
Fine, that's totally fine. So module 6 is acid-base reactions. It ties in a lot with module 5. So there's a lot of things from module 5 that will come into play, and you'll see that today, even in the first part of our 5-week course. There's going to be a lot of mod 5 that links back in with equilibrium, reversible reactions, and whatnot. So content-wise, I always tell my students that module 6 is not the heaviest content module. Compared to mod 5, yes, a little bit heavier, because mod 5 is meant to be the introductory term. So a bit heavier than mod 5, content-wise, but compared to 7, way less, and compared to 8, a bit more. So it's kind of in the middle. It's not the heaviest, but it's middle ground. However, the hard part of module 6 is not the content anyway. It's the calculations. You're going to get hit with a bunch of calculations in week 5 from me. I'm not going to give you too many beforehand. There's one type of calculation in today's session, but it's not the hardest. You would have done it in year 11 already. What's going to be your goal this term? It's this bowl. That is not how I highlight. That is how I draw a red line over my text. What is the goal for today? Today, and for these next 5 weeks, is to reach understanding of the content. So we've got 1, 2, 3, 4 sessions of more content-focused stuff in preparation for week 5 when I drill you with calculations.
Okay.
So I know one of your goals is calcs. We're not going to get onto it straight away. We need to get the understanding first before we do calcs. Does that make sense so far?
Yeah.
Okay. What you're going to learn. What are acids and bases? How do you define acids and bases? And how did that change over time? What are the different types of reactions you can have with acids and bases? Indicators, what the heck titration is, explaining how titrations work, all of these calculations, plus buffer calculations and what a buffer is, how you analyze things with acid and base, and finally, how do acids and bases appear in everyday life? When I read this through this morning when I was teaching my student, I realized I ordered this all funky, so I'm going to rearrange it. But this is the list of content that you're learning, basically. In all the dot points, if I was to boil it down to one little set of dot points, it's this. And the last thing before you start content is how you should study. I won't go into this too much because it's a bit of my own theory that I've constructed over the last 3 years. So take it with a grain of salt. I'm no professor in learning, but this is what I found work best. Learning comes in 3 stages, and to learn something well, you need 3 passes over it. This is like the golden rule. A lot of people actually talk about this rule of 3s, and that's more well researched. But the way I break it down is more into 3 stages. You have awareness, understanding, and then exam readiness. These are entirely different stages, and you can't treat them the same because they're different. Awareness is your first pass over any content. So for example, today, I'm going to be taking you through the first 5 dot points in inquiry question 1, and you're going to become aware of this content. You're going to try your best to understand it and understand it in the moment. But the moment you leave this class, I guarantee you, and if I was in your position, I'd be the same, I'm going to lose 30,
Yes.
60% of it. And that's fine. A lot of people struggle with, they'll step out of a class and feel like they didn't hold anything. It's fine. You're not meant to hold everything. I just want to reassure you with that. The point of today is not to put you into panic mode, and it is not to remember everything either. It's meant to be learn everything in this content, hold 33% of it. That's your goal today. Okay. Oh, Benji's here. Hello, Benji?
Yeah, sorry.
You all right?
Yeah, I had to go somewhere with my dad.
No, you're good. You're good. Are you home now?
Yeah, I just got home.
Okay. We're just getting started on some introductory information.
Okay.
I can send you the recording of the start after the session. So we are recording. Is it okay for you if we record and some of the clips might go online?
Yeah, that's fine. That's fine.
Okay, awesome. So whenever you're ready, just turn on your camera and let me know when you're good to go. In the meantime, we'll finish this brief introduction on how to study Mod 6. So we were just at stage 1. We got awareness, right? Stage 2 is you're going to need to actually understand the content. And this is your job when you go out of class and revise. So using your question solution table, going back through these notes, when you've figured out something you don't know, you can go back and read what I've written for you. That's the second thing. During this understanding, I don't want it to just be reading notes or rewriting notes. I've already made the notes for you. So please don't make your own notes. I beg. It's like the biggest waste of time. I beg. Actively learn. Hello, Benji. Welcome. Miriam, meet Benji. Benji, meet Miriam.
Hi, nice to meet you.
All right, nice to meet you too.
You guys will be in class for the next 5 weeks together.
Awesome. Easy.
And we've just run through a quick introduction of what Mod 6 is. Calculation heavy term. We'll be done with the content by week 2. Your goal is to understand everything by week, or understand all the content by week 2 before you hit calculations in week 3. And then you would have covered essentially all of Mod 6 by week 3 of term. Sound okay?
Yep.
Right. So we're just talking about how you should study Mod 6. The first thing we talked about is getting awareness. So the first pass over content should just be a matter of seeing things and trying to hold about 33% of it. You're not going to hold everything. So don't panic today when I go through a lot of stuff and you don't remember the majority of it. Today's just meant to be quick. You're meant to get all the information past you and you're going to revise it after class. Cool?
Yep.
The second thing that we're just starting to talk about was getting understanding and using active recall to study. I don't know if you guys have seen this online at all. Yes, no? So. Okay. So active recall is not reading notes, rewriting notes, or just doing passive things that aren't really testing you. Active recall is about trying to dig information out from the back of your mind and bring it forward so that you can actually remember and, explain things. So if I was to ask you what Le Chatelier's principle was, going back to our example from before, you should be able to bring that information from the back of your mind and verbalize it now, which is why in class, I'll be essentially verbally testing you all the time to see if you can bring these things up and actively recall. I don't expect you to remember everything, but I expect you, if you get something wrong, you don't entirely understand it, you give it your absolute best to make amends and write it down so that you don't get it wrong next time. You can get it wrong again, but as long as you're making that effort, all I care is about the effort that you're putting in to try recall that information, because there's going to be things that take like 3 or 4 attempts at recall to actually lock in. Okay. Finally, after you've done all your active recall, that can be through things like covering and checking your answers. So you cover it, test yourself, check, is it wrong? Okay, do it again. Flashcards, blurting is where you essentially read something and try to write everything out that you just remembered or say it out loud. Or mind maps. Mind maps are great as well. They're just a bit time consuming. Try whatever, do what you think works for you. You should have a general idea by now, but active recall, absolutely essential for this module. In fact, all of chemistry. Finally, once you've reached a stage where you kind of can recall information, it doesn't have to be fully good. You should get onto this as soon as you can for Mod 6, in particular calculations, practice questions. This is how you get from understanding to exam ready. Without this exam practice, you're not going to be able to perform and convert in exams. I'm sure you've probably experienced in the past when you do past questions from an exam, you feel like you've seen it before. You can just get out what you meant to get out, and you usually score better. There's a good reason for that. You've read the answers. You know what the answers are. That's what the past paper cribs are for. So do practice questions once you get to this end sort of stage. 2 to 3 weeks out from your exam is when you're aiming to start practice questions. And if you get 2 to 3 weeks worth of past paper questions in, I guarantee you your marks will be better, even if you don't see me at all for the rest of your life. This little framework helps with every single subject and every time you learn. I guarantee you, you will find it better. And the last thing, if you want more tips like these and a bit more of an expansion on this model, I've got a study guide on my website. I've spelt this wrong, but it's Catalyst Chemistry and it's online. Get it free. I think you just have to put your email in, but I already have your emails anyway. So you can just download it from there. Any questions before we get started on content? Great. Benji, have you looked into Mod 6 at all yet? It's okay if you haven't.
Not sure. Wait, I have to do something. I'm gonna get my book. I'm just gonna check something.
Yeah, you're right. Okay. Has it been pretty relaxing holiday otherwise, Miriam?
Yeah, pretty much. I probably have gotten to schoolwork a bit later than I should have, but I wanted to make sure that I had an actual holiday rather than
Yeah.
stress all 6 weeks.
That's very important.
I
This is gonna be a
just,
big year. It's going to be a big year. And
yeah.
yeah, you got to give yourself a break this summer before you really get into it. Benji, you're right.
I'm not sure if I have actually.
It's okay if you haven't.
Not sure. Maybe I have, maybe I haven't. Don't remember.
Okay, we'll soon find out because we're starting from the top. All right. So first inquiry question for module 6 is properties of acids and bases. So basically, what is an acid and base? How does it behave? What are its properties? What can you do with them? I guess the first question is, what on earth is an acid or a base? Any guesses? Something about an acid or a base. Shout it out.
The acid is the one that donates a proton, and the base is the one that accepts it.
Hey, I like it. Miriam, anything else?
Acids are pH less than 7, bases are
I
more than
like
7.
that. Great, perfect.
It's
Anything
also
else?
on the sheet in front of us.
Yeah, I can see, but things that are more familiar. You're going to say the things that are more familiar. So I have a better idea of what's not familiar. Little cheeky technique there. So an acid or a base, Benji's gone and given us a sensational definition of what an acid is. In fact, it's one of the definitions we need to know. There are several definitions of what an acid and base are, and it's changed over the last 3 or so centuries. But for now, what we'll start with as a definition for acid and base that makes it very easy is an acid is a compound which forms hydrogen ions in aqueous solution. So whenever you see an acid, acids usually will have a H attached to them. So hydrochloric acid is a HCl, nitric acid is a HNO3, as you can see, right? So acids, hydrogen ions can be released in aqueous solution. Bases, we're talking things that release hydroxide ions, so OH minus. Bases release hydroxide ions in aqueous solution. And these are the starting definitions we'll start with for acid and base. Okay. The only other term that's a bit strange is alkalis. You might see this. It just means a water-soluble base. So for example, if you have a 0.1 molar solution of NaOH, that is a alkali solution of NaOH. That's all. Now, we have some essential acids and bases we should know. If we don't know them yet, we've got plenty of time to learn them, but we need to get to know all of these. So we're going to have a quick quiz. How familiar do you feel with these, Miriam?
Not super familiar. Probably the first couple, but
Yeah,
after that it
okay.
gets a bit.
All good. And Benji, how are you feeling?
Some of them.
Some of them.
Some.
Okay.
No.
I'm going to give you 30 seconds each to read over this table. Write down any notes you need. Remember as many of these as you can. Go. For 10 seconds. All right. If you wrote anything down, turn over that piece of paper. And now, let's see what we remembered. Miriam, what is the formula for hydrochloric acid?
HCl.
HCl. Benji, what is the formula for nitric acid?
NH3. Oh, wait,
Pardon?
is it? NH3?
NH2, not quite.
NH2. Oh, shit.
Not quite. Nitric acid is, think, whenever do you remember your polyatomic ions from year 11? Pretty blurry. A little bit blurry.
A little, yeah.
Yeah. So most of these acids are actually just rearrangements of those polyatomic ions. So
Mm.
nitric acid is nitrate with a H in front. Sulfuric acid is your sulfate with a H in front.
Mm.
Carbonic acid, carbonate with a H in front. Phosphate, phosphoric acid. So you need to make, if you make these little associations, which I'll give you along the way, these little gems, and you hold them, it makes things easy to remember. So the first one is most of the acids are just your polyatomic ions with a H. So let's go on to the next one. What would sulfuric acid be? Open to the floor.
Oh, H2SO4.
Beautiful. What is phosphoric acid?
H2.
H3PO4.
Oh,
H3.
H2PO4.
H3. Good.
NSP123.
Yes, good. So you've got some associations of your own, I see. Good. Let's go acetic acid.
This one's really hard.
CH3COOH.
Yes, chiku. Chiku makes it easy. And lastly, if anyone can get this one, citric acid.
That's the last one where I was
Yeah.
like, oh, I'm not going to bother doing that one. I'll figure out the rest of them.
Citric acid is a nutty one.
It was C6,
yeah.
H8,
Ooh.
something 7. Was it 07? Something
07, good.
Oh, okay.
Citric
Good.
acid, C6H8O7, the wackiest acid out there. This is a very common one they trip people up with in exams because no one knows what citric acid is. Like, how are you going to guess this? But the important thing with citric acid to remember is it has a property called, we'll touch on it later, but citric acid is an important property we'll learn about later, and I'll bring it up then. So these are your acids. Pretty much all of them, no, we did cover all of them. When you were reading over that list and trying to write things down desperately to hold it in your brain, did you feel how it was a bit different to when you're just reading over notes or anything like that? That's the feeling you should have whenever you're studying. That is active recall. Passive study is when you're just glossing. That active feeling of trying to lock things in and being like, oh my God, I don't remember. You need to be in that feeling more often than not. And if you're not, take a break. It's fine. The bases are a lot easier. There are two main types of bases that we deal with, hydroxides and carbonates. So sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, anything, any metal with hydroxide, base. Carbonates, base. Sodium carbonate, magnesium carbonate, all the same, metals with a carbonate. And the last important base is a base called ammonia, NH3. Does anyone know the alternate form of ammonia?
Ammonium.
Ammonium.
NH4.
Good. And what charge?
Oh, is it minus?
It's plus, but good. Ammonium NH4 plus. And we'll realize later on why ammonium is actually an acid. Do you notice how ammonium has one thing different to ammonia? What's the difference?
One extra hydrogen.
An extra hydrogen. So it allows it to act as an acid. Talk about it in due course. Properties of acids and bases. We've talked on the pH already. As Miriam said, pH less than 7 for acids, bases pH greater than 7. But there's some other properties that we do just have to sort of know. They can ask these in multiple choice contexts usually. So acids taste sour, bases taste bitter. They can both burn skin, but they have different names. So corrosive versus caustic are the different names for acid and base respectively. They both are conductive. And I've asked you guys, what actually is conductivity? This is really a strange concept. What is conductivity?
It's the ability for the electrons to flow in the solution.
I like it. Benji, anything to add on top of that?
No, that'd be what I'd say.
Yeah,
Free flowing electron.
yeah. And you guys are both right, but we haven't covered all cases. Free-flowing electrons is true. So that'd be true in something like a metal. A metal has delocalized electrons, which can move from one side to the other, right? But what about, say, a solution of water with salt in it? Is that a conductive solution? I'll tell you it is. Why is it conductive? Why is a salt solution conductive? What does it have?
Hydroxide ions.
Not quite hydroxide. I mean, it would, but the main thing that's carrying charge is not the hydroxide. We put
Okay.
salt, so NaCl. What happens to that?
It breaks up.
Yes. Breaks up into what?
Na and Cl ions.
And what state are they in? For bonus points.
Oh, solid.
Once they've broken up in solution, and if you put salt in your pasta water, do you still see the salt? What happens to it?
Like aqueous
Dissolves.
solution.
Aqueous, dissolves. Great, perfect. So you're dissociating NaCl into Na plus aqueous and Cl minus aqueous. And they're going to sit in solution as ions. Ions. And this solution is conductive because charged ions are able to move around freely in solution. Okay. So the property of conductivity can be simply defined as the ability for a solution to move charge through free moving charged particles. Something like that is what I would define conductivity as, because something like a metal, yes, it has electrons, it can carry. A salt solution with NaCl, yes, again, it can carry charge because it's free moving positive Na plus and negative Cl minus. Is water, pure demineralized water, conductive? Having said that, deionized water, is that conductive?
Well, if it's deionized, it doesn't have free flowing charged ions, so no.
Yeah, correct. Water itself is not a conductive liquid. What makes water conductive when you bring it out of the tap is your ions. Your fluorine the government put in to keep our teeth clean. Chlorine, sodium, all your different electrolytes floating in there are carrying charge. So when you have water out the tap, yes, it's conductive, but water itself is not conductive. Water, H2O, has no charge. Does that make sense, guys?
Yep.
Okay, any questions so far? Anything at all? And Benji, I said at the start, the point of these sessions is to go quick. So the moment you don't get something, you stop me, I explain it again.
Yep.
Ask questions as soon as you can, because it's the only way you can get clarity.
Mhm.
Fourth point, acids turn blue litmus red, and bases turn red litmus blue. What is litmus? What is litmus?
Isn't that something with the indicators?
Yeah,
Yeah,
good.
I don't remember, but I remember that. No, I don't remember that much. I remember it's like universal indicator, and that
Yeah.
litmus is the color that pulls out. That's what I remember.
Yeah, no, you're on the right track. Litmus is what we call an indicator. We'll learn about these in a second too. Indicators tell you when you're in basic or acidic range based on their color. So litmus in basic conditions is blue, and litmus in acidic conditions is red. That's all it is. And lastly, the pH points. There's some points on naming acids, which I'll just go through quickly anyway. When you have hydrogen ions associated with an anion, so this is hydrogen and chloride, hydrogen and fluoride, or your hydrogen and bromide, for example, we name them in a very specific way once they become acid in aqueous form. So if you dissociate in this solution, if you dissociate these compounds in solution, they then become an acid and you name them as such. So if you have HCl gas flying around, we don't call it hydrochloric acid. We call it hydrogen chloride. As soon as you dissociate in solution, no, sorry, not dissociate. As soon as you dissolve in solution, you have aqueous HCl, and that dissociates into H plus and Cl minus as the acid. We then name it differently. So as you've seen, it's going to be called hydrochloric acid in the end. How do we come to that? We drop the "ide" from chloride and replace it with "ic." So chloric. and we just change the hydrogen to hydro, and it becomes hydrochloric acid once it's in solution. So in water, it's kind of confusing because it's still technically hydrogen, but you can remember it as hydro. It's now in water. Oxyanions ending in 8. If you have something, all your polyatomic ions are going to be nitrate, sulfate, carbonate, right? They end in 8. When you have any of these, all you need to do is change the 8 to ic once you make it an acid. So nitric, sulfuric, carbonic. Any questions on those? These are the easy ones. The last one's a bit odd and brings back some of year 11 trauma into the mix. Reduction and oxidation. When you reduce one of these polyatomic ions, your oxyanions, when you reduce one of them, you end up with a different polyatomic ion. So for example, with nitrate, NO3 minus, if you reduce nitrate and turn it into nitrite, which has an oxidation state which is lower, you don't need to remember oxidation states. Do not worry about that. That never comes up again, basically. You name it differently. So instead of nitric acid, you replace the nitrites ite with us. So this becomes nitrous acid. Whenever you see something that looks like a polyatomic ion, but isn't quite. So you can also have sulfurous acid with SO3. That's also possible. Think if it ends in ite, it goes to us. If it ends in 8, it goes to ic. And then hydrochloric for the anions. Any questions on those namings? A bit to take in.
Mm.
These rules aren't so important going forward. I never think of these again. I just remember these are my polyatomic ion acids. So I remember all of those. And then I'll remember their associated ones are just going to be, instead of ic, it will turn to us. And that covers most bases. You're not going to see these ones very often at the bottom. These are very rare, but I just include this so you have knowledge of what's happening there. Because this bottom point took me about 3/4 of year 12 to understand. I never got around to it. Okay. So that's like the foundations. That's just what an acid is. What are some of their properties? And how do you name them? Benji, all good?
Yep.
Any questions, Miriam? Okay. If you guys have no questions, you must understand everything, right?
Yeah, sure.
Yeah. Okay, let's move on to indicators. So you'll notice as well with how I'm structuring my notes, they go by the dot points in the syllabus. Do you guys use the syllabus very often to revise?
Yeah.
Yeah. Miriam? Not really. That's going to be the number 1 hack you have. Benji, what does the syllabus tell you?
It tells you all the content that's going to be on the test.
Yeah,
They
it
can't
tells you
deviate from it.
tells you an exhaustive list on everything your teacher can possibly test you on, right? So by the end of this term, you're going to have my notes, which have things written out under every single dot point. Revise these. It's so easy, but some people never get told that the syllabus is everything you need to know. And it pains me when I talk to someone in like term 3 after struggling for 3 terms of chem. They come to me like, I don't understand how everyone knows everything. It's in the syllabus. It's all there. These dot points are taken straight from the syllabus at the start of the notes. So for example, this one is to conduct an investigation and demonstrate the preparation and use of indicators as illustrators of the characteristics and properties of acids and bases and their reversible reactions. It's basically make an indicator, explain how it works, and tell us what it tell us how you can differentiate an acid and a base using an indicator. That's what we need to know from this dot point, and that's what we're going to talk about. So an indicator, how would you define an indicator, Benji? Starting from that, what do you reckon it would be?
How do you define an indicator?
Hmm.
It has like a range of colors when you put an acid on it. I don't know.
Has a range of colors, yes. One of them is pink.
It indicates what pH level it is, depending on
Yeah.
this color you get when you put an acid or base in.
Yeah, basically, it tells you what the rough pH of environment is based on the pH range of that indicator. So indicators will tell us whether we have an acid or a base. It's going to tell us roughly the pH range based on what its pH range is. Okay. Some examples of indicators. There are 4 indicators which I suggest you learn because they are high yield. Okay. When I say that, I mean it. When I say those things and I pull you up on high yield, I mean it, because this will help you immeasurably. There are 4 indicators which you need to know. You need to know their names, their pH ranges, and also their colors over the pH range. If you know these, essentially this table, you'll be able to answer any indicator question that asks you for an indicator or any question that quizzes you on an indicator. You'll be able to draw on this table. Just give you a moment. Don't feel like you have to write out the whole table though. That's not needed. But this table is very helpful, and I use it all throughout my year 12 as well. Okay, you right soon, Benji? You good?
Mhm.
Okay. So the 4 indicators: methyl orange, bromothymol blue, litmus, which we've already heard about today, and phenolphthalein. 4 really strange sounding indicators, but they are important. So what you'll need to remember is methyl orange, its pH range, 3.1 to 4.4. And what colors the indicator will be on either side of that pH range. So below 3.1 or above 4.4 and between 3.1 and 4.4. That is what we call the transition range. So this whole middle column in the middle is what these indicators would appear as if the pH of the solution they're in is within these ranges. Does that make sense? So if methyl orange, Miriam, is put in a solution of 4.5 pH, what color is it going to be?
Yellow.
Yellow. Benji, if I put this in a solution that is pH of negative 0.1, what is this going to be?
Red.
Red. And in between 3.1 and 4.4?
Orange.
Orange. Great. You notice how I said negative pH? Negative pH of 0.1?
Yeah.
Is that possible?
Yeah, it is, but it's just really rare, and they don't
Yeah.
do it.
Yeah. So pH, a lot of people come in with this conception that pH is limited to 1 to 14. I'm going to break that conception now. It goes beyond. You can go to negative pH. You can go to pH above 15. It's possible. Just very uncommon, as Benji said. So be aware of that as well. Bromothymol blue, same kind of thing. It's got its pH range. You guys know how to read it now. It's got its own colors. And same with litmus phenolphthalein. I'm not going to go through them each. What I will get you to do, though, is have a look at the colors in the acidic range. They're mostly towards red, right? So if you were to pull up a full color spectrum going from red, Roy G. Biv, so red, orange, yellow, green, blue, indigo, violet, that's your color spectrum. Your acids will tend to have indicators which appear more towards the red side, whereas your basic indicators, or the basic side of indicators will tend to be more towards the blue. So we can see that with methyl orange, red compared to yellow. Bromothymol blue, yellow compared to blue, all the way over here. It's typically like that. There's some exceptions, but for the most part, acidic indication will be in a redder range, basic will be in a bluer range. And we've already talked about how to read indicators. You guys kind of figured it out on your own, which is great. Now, the question. I'm going to give you both a minute to figure this out, and you're going to have a go. What is the pH range of a solution, which is each of these colors in these indicators? Give me the narrowest possible range of pH you can determine when you have each of these colors with the indicator in the solution. I'm going to give you a minute. How are we doing? Any ideas?
Okay.
All right. Anyone confident in the answer?
I am.
All right. What's the range that you
Greater than 7.6, less than 8.0.
are we in agreement, Miriam?
Yep, that's what I had.
Beautiful. So you guys now know how to read indicators and narrow down a range. Did have to explain it to you. It's all very intuitive when you got the understanding, right?
Yeah.
What you will get in the exam though is not this table. You will just get this question like that, which is why I tell you it is essential you remember these indicators back to front. If you don't know the ranges, you don't know the colors, you are essentially screwed. So remember the ranges, remember the colors, remember the names. As a bit of an extension, how does an indicator actually work? And what is an indicator even doing in solution? And if you've gotten a hint any from the title at all, indicators are equilibria. They're equilibria systems. So mod 5 coming back into play already. The general form for what we say an indicator is this. An indicator tends to be what we call a weak acid or a weak base. We'll come to understand those terms a bit better as we go. But for now, what we need to understand it as is that a weak acid will only partially ionize in solution. So it's going to form, say, 5% of its amount will dissociate in solution only. It will not dissociate 100%. When an acid dissociates 100%, we call it then as opposed to a weak acid, a
Strong acid.
strong acid. Good. So we've got two forms of acids. We're talking about weak ones here. And indicators tend to be weak acids, and they can form equilibria. When we're in an acidic pH range, we put our indicator into, let's say, hydrochloric acid, a ton of it. In hydrochloric acid, what do we have present? What ions?
Hydrogen and chloride.
Perfect. Hydrogen and chloride ions. Think about how that affects this equilibrium of an indicator. If we have a lot of hydrogen, can someone explain how this makes sense in LCP that it would shift left? If you have a lot of hydrogen. Miriam, you want to give this one a shot?
Oh, just a quick question.
Yep,
The
go.
HA and the A minus, what are they
Yes.
stand for?
Oh, great question. Sorry. Good.
Isn't that a hydrogen acid and then hydrogen and then acid minus?
Yes. So HA, sorry, I should have clarified this.
Oh, good. Oh, good.
HA means H attached to any acid. So A is the general for an
okay.
acid. Yeah. And A minus in this case is a base. You will often see base represented as B as well. So BOH would be a general form of a base. Got it?
Mhm.
Very good question. Keep asking them. So if you have a lot of hydrogen from the HCl, how does that affect the equilibrium in terms of LCP?
Well, it'd want to shift right because it wants to balance the equation, and if there's too many hydrogen, it's gonna give them over to the other side in order to make it more balanced, whatever it is.
Miriam, would it shift right or left? And
It
why?
would, I think, left, the reverse reaction,
Why?
because you've got more hydrogen, so you've got more to react. So you need, how do I explain it? Yeah, there's more on the right side, so
Hmm.
we'll be able to create more on the left side.
What do you say to that, Benji?
Yeah, I messed up.
You're all good. Does it make sense though?
Yeah.
Yeah. So I think your understanding was right. We just said the wrong direction. But if you have more H plus in solution, the change is a ton of H plus comes in. We've got way too much H plus. The system says, I hate it. It's positioned too far to the right. It wants to get rid of that H plus however it can. And the only way it can do that is by shifting to the left to decrease the H plus, to decrease the A minus as a result of that, and increase HA. So what have we done? We've gotten rid of A minus and we've produced a bit more HA. We've gotten rid of all the A minus, in fact, because there's so much H plus. So how is that going to change the color? We've gotten rid of this A minus, which is typically blue. And we've made a lot of red because it's in acidic conditions. So the acid has caused this indicator to shift to the left and show us its acidic form. Vice versa, what would happen if instead you added base to this? What would happen if you added some OH minus, some mad sodium hydroxide into this system down here, and you neutralized off all of this H plus and more? What would happen if you got rid of all of this H plus with some sodium hydroxide? Where would we now shift?
Gonna go to the forward direction and go blue up.
Yeah, it's going to go forward because now it's like, oh, I need my H plus back. Shifts to replace that H plus in accordance with LCP because the system's been disturbed. Bring back up our A minus, decrease our HA, and bring back some H plus. And then we go blue. So the way an indicator works is it's an entirely reversible system that goes forward and backward, depending on what condition you put it in. Does that make sense?
Yeah.
Any questions? Miriam, you look a bit confused.
Yeah, that's my thinking face. So if we're adding A and getting rid of all the H, we've got lots of HA, which is typically redder. But we're thinking that the H plus here is bringing that red color to make it go blue.
The A minus is making it go blue.
Mhm.
I think I confuse it with what's reacting.
There's
Yes.
too much HA, so there's too much HA, so you're gonna put the A over and add H plus to like what's the type of reaction where you break it apart and then
Dissociation.
yeah, and because there's more A minus now, it turns more blue.
Okay,
Yep.
that makes
Does that
more
make
sense. Yeah.
And I should also be clear what neutralization is. We haven't covered it yet, but it's this equation down here. This is what we call neutralization. It's where you react H plus with OH minus to form water. This is neutralization. And this is what we talk about every time we say we have a neutralization reaction is this. This general equation is happening. We say neutralization. Very important equation. Very referenceable as well. Very easy.
Mm.
Okay. The last case. So we talked about the acidic range, that we just talked about the basic range when you add in a bunch of OH minus. What happens when you don't really have that much H plus, you don't really have that much OH minus. In fact, you sit right in the middle. What do we have present in solution from the indicator? We have a bit of everything, don't we? So then, does that explain then why our color in the transition range is always just the intermediary of the two? It's just a mix of your acid and base form. So if you have red acid, yellow base, you're going to get orange transition because it's right in between. Does that make sense? Any questions? They're good. Keep them coming. Okay. There's a practical you're going to do this term. You might have done it last term. Has anyone done it? The red cabbage prac?
Yeah, I did that.
Did
My
it?
class did, I was away, but yeah.
Okay, great. So all you need to understand from this prac is basically how it worked. And sort of we can apply what we just talked about to the indicator. But what you need to understand are the process of making a standard, some details about boiling the cabbage and cooling it and whatnot, and then testing each of the indicators with your standards. So first of all, what is a standard? Does anyone remember what a standard solution is? How do you define it?
It's a solution you know the pH of, but
Well,
there's
not quite pH. You're on the right track. It's a solution you know something
oh,
of.
the moles.
Moles, be more specific.
Like the moles of acid in solution.
Would know it, but usually we refer to it as the concentration.
Concentration.
Concentration,
Okay.
good. So you know the concentration of a standard solution. That is the most important part here. You know the concentration. All you're doing in step one for this prac is preparing a bunch of solutions which span across all the different concentrations from 10 to the -1 to 10 to the -6 molar of acid and base. You're doing it for both of these. Because what that'll actually get you is solutions of pH 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You get a full range of all of the different pHs that you can test your indicator with. Do you remember how to make primary standards, roughly?
Roughly, yeah.
Roughly, Benji? No? Okay, let's go
really.
over it. Let's do it. So with a primary standard, what you're trying to make a known concentration. Does anyone remember the formula that gives us concentration?
Oh,
N on M, C equals N on M, number of moles on the
We've got,
mass.
we've got one bit right.
N on
We've got
V, the
N on
volume.
V. C equals N on V. C equals N on V. So to find concentration, we need two things. We need the moles and we need the volume. How do we find the moles of, because what we're going to be doing is putting a bit of solid into a certain special flask and essentially filling up a volume. So how can we know how many moles of solid we had?
mass over mole mass.
Molar mass. And what can we measure? What do we actually measure to turn it into moles?
Or how much it weighs.
Yeah, so you weigh out amount of solid, say you have 2 grams. You can convert that mass into moles using the formula you referenced before, Miriam. And then, so now you have your moles from the solid. The last thing you need is a volume. Is there a special flask you guys might have seen around that can give you a volume?
Mhm.
What would that flask be named?
Volumetric flask.
Volumetric flask. So a volumetric flask completes the second part of our primary standard preparation. It gives us our volume. Because from that point, we can go C equals N over V and find our concentration. Does that first step make sense? So we're doing that for all of these different concentrations. The next steps, you're just chopping up cabbage and boiling it. The only thing to note when you're boiling this cabbage in this prac, and I'll throw out these little examinable little details every now and then. So I'll doggy ear them. You can get tested on how hot can your solution of red cabbage be when you boil it. It cannot go above 120 degrees Celsius because the indicator denatures and it becomes useless. So that's just things like that are things you'd only get from having done exams. You would never, ever in your wildest dreams imagine that you need to know that detail from just reading a textbook. You're like, that's insignificant, but it comes up in exams. Okay. You would have made a solution, you strain it, you collect the liquid, cool it, and then you're essentially just placing bits of these primary standards into your solution, and you're testing out the pH ranges. And it should look something like this. You have a big spectrum of all the different colors, which comes out really nice. And we've essentially done the prac at that point. That's it. Does that make sense? Any of these steps not really clear? All good?
I remember this now.
Yeah, you remember it now? Okay.
Put it in the test tubes and you drop the acids in the base and the colors.
Yeah, exactly right. And Miriam, if you want to go watch it on YouTube afterwards, there's definitely recordings, so feel free. Risk assessment, very, very simple stuff. Don't put acid and base in your skin, wash it off, wear PPE, things like that. And obviously you're working with a naked flame if you're boiling something, so don't burn yourself. Yes. So what's happening here? This is now the important part of this prac. This is probably the most important part for me as a teacher. I want to make sure you understand what's actually happening. And I can't emphasize enough. For pracs, I think I wrote a little foreword at the front. Okay. First thing, you need to have fun. You need to enjoy your pracs. I'm not about just like go in there and grind. Enjoy it. Chem pracs are like genuinely some of the best times you have in school. Unironically, they're so fun. But your main mission is to actually understand the chemistry of what happens in the prac, the equations, the calculations. What's actually happening is your goal. If you just go in there to follow the steps and be like, okay, I made some solutions out of different colors. No, it's not going to help you. You need to understand actually what's happening behind the scenes. And if you don't understand, you need to ask your teacher, you need to ask me what's going on. Is that fair enough?
Yep.
So what's happening? It's these two equations. What are we looking at here? What does this resemble from before?
The H2 anther thing is your acid. And then, so that's like HA, and then the other side's like H plus A minus.
Yes, perfect. So this is your H plus, albeit in a different form, and this is your A minus, although it also has a H, as you'll see. So this second equation is just the same thing. HA, H plus, A minus. It's a weak acid, weak base pair forming the indicator. The only thing you'll notice that's different is that we have this thing, a H3O plus and H2O. Has anyone seen this before? H3O plus, what's this?
Hydronium, no?
Hydronium. So Miriam, this is what we call hydronium. And in solution, when we actually have an acid that's dissociated, it doesn't form H plus. I mean, it does, but it doesn't exist as H plus. It forms H plus and instantly will react with water to form H3O plus,
Okay.
which is hydronium. Hydronium H3O plus. So what's happening here? Say we add this indicator into a wildly basic solution. What's going to happen? In terms of not LCP anymore, can someone explain the first line in terms of collision theory? What's going to happen if you put this into, oh no, let's start acidic first. You put this into an acidic solution, what's going to happen based on collision theory? Mod 5, mod 5.
Oh, oh, wait, say it again. Wait, so you're putting an acid into that.
You're putting this indicator into
Yeah.
some acidic solution. What's going
Okay.
to happen in terms of collision theory? Have a go.
Put it in this. You're gonna have. Wait, that doesn't make sense to me.
Okay, we'll start first of all. What does collision theory tell us about?
Collision theory is about your rate of reactions. So
Hmm?
like your surface area, the concentration,
Hmm?
and like the activation energy and all that stuff.
Yeah. So there's a few arms to collision theory, but the main thing that you need to know is that it's about reaction rates, collision theory. And it's related to LCP, but not the same. So LCP, you may have seen in mod 5, hopefully, that you get asked questions where you're asked to explain the changes in equilibrium based on LCP, and also you get asked how to explain it in terms of collision theory. Is that something you guys are both familiar with?
Yeah.
Yeah. So I'm asking you to do the same here. Before, we just explained the shifts in this equilibrium in terms of LCP. LCP explains the shifts in equilibrium from a principle standpoint, like rules. If you disturb the equilibrium, it's going to resist that change. That is an outcome-based explanation. Collision theory explains why that's the case. Why are we shifting towards the side that has been decreased in concentration? Why? So that's how they're different. LCP is explaining the rule. Collision theory explains why the rule is true. So if I put this in a solution that is acidic, what part of this equilibrium is going to be disrupted? Put it into a solution with heaps of HCl. What is going to be disrupted?
The H2 antho. There'll be heaps of it.
Ooh, almost. You're on the right track. You're thinking there's going to be a lot of acid, right?
Mhm.
When we talk about lots of acid in solution, we talk about the H plus, we talk about the hydronium. Yeah, because because HCl, that's going to dissociate into H plus, which is going to turn into H3O plus.
Yeah, okay.
So we have now lots of H3O plus coming up. How does that affect rates of reaction?
There's more, the higher concentration on the right side, and
Yeah, yeah.
as LCP says, the rate of reaction on the
no.
right side. No,
Don't mix LCP collision theory. They're different.
the different.
Just
No,
tell
but
me
like
collision theory.
the rate
Yeah.
of reaction is greater on that side.
Yes.
So
Why? Why? Why is it bigger?
because there's more concentration, so there's more collisions. And I just realized that equilibrium is based on rate of reaction, and because
Yes.
there's more collisions, and because the rate of reaction is higher on the forward reaction, it's going to favor the reverse to get more H2 antho, and that's why it'll come out as red or more acidic.
Yes. Does that make sense?
Yeah.
Miriam, I'll explain it one more time. I got the confused face again. I'll go one more time. So, because this is so important, and so many people never understand this. H3O plus, what you did when you added this into HCl is the H3O went bang up through the roof, right? So how much, compared to before when everything was like at constant concentrations, you've now gone H3Os through the roof. Is the reaction rate on the reactant side going to have changed? If we just add in H3O, no, it's not going to change. Has the reaction rate in the reverse side changed? We've gone H3O up.
Yeah.
We go up, right? Because now we have so much H3O, this H antho, wherever it goes, it's just going to hit H3O and react.
Okay.
Fast enough. So you have more collisions between H3O and H antho. And if you remember,
This reaction is going faster.
the reverse reaction will go faster because you have more successful collisions proportionate to the forward reaction.
Mhm.
You have more reverse reaction collisions compared to forward reaction collisions before. And so the equilibrium will shift which way?
To the left.
The left. Collision theory in a nutshell.
Cool.
Sense?
Okay, that makes perfect sense. Yeah.
Yeah. So collision theory and LCP very closely intertwined. They're explaining the same thing. They just explain it differently. And if that makes sense, then like that's basically all of mod 5. I'm not gonna lie. Mod 5 isn't too bad. Okay. That's basically all of this that I've written underneath. So if you need to come back to it, just read through what I've written under and it'll make sense again, hopefully. But if that made sense, then let's move off of indicators. There's a practice question here, which you may want to test yourself on. It's basically the same thing with methyl orange going to a red color as opposed to orange. And you just explain what would happen in either case if you were acidic or basic, what's happening to this equation. Feel free to give it a go. We're not going to do it now though. Actually, no, I want to see how both of you write because I haven't seen you write too many responses. So what I've done, Benji, is there's a Google Doc I've added you to. And we're going to try this question together in here. So let me know if you can see this doc, and same for you, Miriam. You ran it before, I think.
Yeah, got it.
Okay. Let me know if you can see it again.
Okay, yeah.
Yep. And can you see it, Miriam, on your end? Because you'll need to type it in a second, that's all. Okay. Oh, we'll wait for a second. There we go. So the question is, when a few drops of methyl orange are placed in solution, the following equilibrium is established. And it shows this schematic almost of methyl orange and its counterpart red form. So the question asks, with reference to Le Chatelier's principle, explain how methyl orange functions as an acid-base indicator. How does it do that? So before we write anything, let's make a bit of a plan and discuss it as a team. How are we going to structure our response to this question? It's 4 marks. What are we thinking? What's going to go into this?
You'd probably show that base equation of the thing.
Yep,
You'd
that would be
show an
very useful.
equation. And
Yeah.
then would you do separate cases?
I like that idea. What kind of cases might you do?
So
Any idea?
you'd have a case where the thing's more acidic, a case where it's more basic as well.
Yep.
And then you could do the HA verse with sign, H plus A minus. And then you could do the same thing with base, right?
Yep.
And then you'd put that in, and then you'd explain why the indicator works like that. So like for the
Yeah.
HA plus 1, you're like if you add a more acidic, when like say you add a acid like hydrochloric acid, if you add more H plus, the Satyala's principle says you reverse favor, and then
Yeah.
you indicate more red.
Yes. And then so the overarching message of what I was trying to get you to say there, and you did say, was that the structure should be in 2 parts. You need to explain what happens here. And before any question, you need to think about what your structure is. Because if you don't hit the structure right, you don't hit all the parts, you're never going to score full marks, no matter how well you explain things. So structuring responses, I'll teach you a little hack as well for exams. This is way, way, way away, is you can actually score marks off making plans. It's crazy. In physics, I made a plan for a 5-mark question. I did nothing more than write 2 sentences because I ran out of time. In my, I think it was like my second assessment, I scored 3 out of 5 for writing a 15-second plan because it hit the right points. It was like a very succinct plan and it just told the marker what they need to know for those 3 marks. Like obviously it wasn't 5 marks, but for a 15-second plan, like I'll take it. I'll take it. What you do in a plan is you essentially label out your structure. So here, as Benji said, the structure is probably going to be acidic case, basic case. And you say in acidic case, it turns, which way is it going to go? You have to really look at these. Oh, the acidic one's the bottom one, the red one, of course. So acidic is going to be red, the bottom one, and basic is going to be, question's gone, orange, and the top one. This already tells the marker I know which way this is orientated. I can probably score a mark for this. And you don't really, and you can obviously explain it more in your plan, but I just go straight into it from here because I'm pretty confident from this plan I know what I'm talking about. And I just write it from here. So you have the acidic case, the basic case. Maybe what I'll do is I'll get you guys, can one person write the acidic case, one person write the basic case? Any volunteers? Be wise. Acidic case?
I'll write the acidic case. I think I'm a little bit lost, but I think I'll understand once we see.
That's okay. And Benji, do you want to try the basic case?
Sure.
Okay. So Benji, while you do that, Miriam, which part of it is confusing you now?
Just I think how I would answer it, I'm not quite sure. So the acidic case is methyl orange going into an acid.
Mm-hmm.
I'm not quite sure I understand the diagram.
Yes. So the diagram, am I still sharing my screen?
Mhm.
Okay. The diagram, it's a bit zoomed out. Maybe I'll go into this one over here. The diagram shows 2 organic molecules. These are nothing you would have seen before.
No.
But what you can see is that one has, if you look along the whole chain, one of these has an additional H compared to the other. You can see here. The
Yeah.
next. So from that, I was able to tell that this is the acidic part.
Mm-hmm.
So then generally, do you remember what the general form of acid dissociation was from before? When you asked that really good question about what something meant.
Oh, the HA.
Good. Which of these is HA?
HA is well the bottom one with the
Yeah,
acid.
the bottom one. This is HA.
Mhm.
This is A minus.
Okay.
HA, A minus. And you explain it the same as before. That's why I give you the general one. Everything is an application of that. Does that make a bit more sense?
I'm not quite there, but I
Okay.
think I'm getting there.
So then, and Benji, just have a go at this while we talk through this as well. When you add this into this whole system, which is a little bit of the top molecule, a little bit of the bottom molecule, into a system that is acidic, it's going to have lots of what again?
Acid, HA.
It's going to have lots of, I think that's what's confusing.
Okay.
Because remember when we talked about adding into a solution of
Oh,
HCl?
H3O.
Yes, good. You're going to have lots of H3O plus. And what was that called again?
High something. Genium?
Hydronium.
Hydronium.
Good. So you're going to have lots of that. How does that affect equilibrium? I think just because this H is here, this is what makes it a bit confusing.
Mhm.
This H should be up here as a plus with this.
Okay.
So if you have lots of H, how's that going to affect the equilibrium?
Lots of H, which means we've got HA on this side, H3O on this side.
Yeah.
Is that everything? There's more, isn't there?
There'd be a water as well, but we don't
Okay.
have to do the H3O form. We can just do the H plus form.
H plus, okay.
Let's do
HA, H plus. We've got lots of H plus here, so we're having a faster reverse reaction. So we've got lots of HA now, and we've. Oh, thank you.
Yeah, this will probably help. A minus.
That's what I'm missing. Okay.
Yeah.
So we've used up the A minus. We've got lots of H and lots of HA.
Mhm.
Signs.
And HA is our red.
HA is the red, correct.
So the color will go red.
Why? In
Because
terms of LCP, why?
In terms of LCP, we've got lots of H from our acidic environment. So because this is an abundance of H, we need to balance it out. So the reverse reaction will go faster, using up our A minus. Which will then produce a lot of HA. So the A minus is the blue, or in this case,
is orange.
Orange. We've used up all the orange, but we have an abundance of red.
Yes.
Okay.
That's the gist of it. The only thing I'll say, when you're talking about LCP, this is an LCP response. We don't want to talk about rate. Because remember what rate is? Rate is what explanation?
Collision theory.
Collision theory. So don't mix the two. They don't go together. They're separate. Do not mix rate and LCP. Okay.
So what's the best way to say?
I'll type it out and I'll show you what I would write. So I would say, by adding, I'll copy Benji's wording. By adding a acidic solution to the methyl orange indicator. Yeah, I'll give an example too, such as HCl.
Mhm.
The concentration of H plus would be increased.
Mhm.
Would be increased. I guess you could tag on disturbing the equilibrium.
Okay. So better to think about it in terms of concentrations and favoring the reactions.
Yes. Better think about which side has had a change. How are you going to resist that change? If you've increased one part, how are you going to resist that? You're going to decrease it. So which way do you have to shift to make that resistance?
Cool.
Okay. So the concentration of H plus increased, disturbing the equilibrium. In accordance with Le Chatelier's principle. If a question asks for this explanation, you give it. You give a definition of LCP. So Benji's done that as well. In accordance with LCP, how do you define that, Miriam, in your own words?
LCP?
Yeah.
Which states that a disturbance in equilibrium results in like an opposite change.
An opposite change? True, but it could be a bit more refined.
The equilibrium will shift to, I don't know how to say it, but like to make it equal, to
shift to counteract.
Counteract. That's a great.
Counteract
the change.
Change.
Okay.
Thus, what happens?
Thus, Do you want an appearance or like a?
Yeah. So what's happening? What's
Thus,
going to happen?
the liquid will be red or show red.
And then what's the shift in equilibrium? When we talk about,
Oh, thus the equilibrium will shift towards the reverse reaction or to the left, resulting in a red shift or a red color for the solution.
this is what we're looking for, right?
Okay.
Does that make sense?
Yeah,
It's probably a bit
that makes sense.
because I was just trying to apply what we were doing, what you would have done last
Yeah,
time
yeah.
now. So does this make sense how it's all kind of intertwined a little bit?
Yeah, yeah.
Okay. Benji, did you see that first one as well?
Oh yeah, that's it.
Okay, we'll have a read through your now. So Benji's gone with base dissociation by adding, ooh, hang on, Benji, one thing.
Oh,
H with a B. What does a
Right.
base have?
it's not right. Hold on. Oh, it's a hydroxide.
Yeah. So the general form of base is a bit different. We don't necessarily need this equation. Sorry. We don't necessarily need this equation, but we can do it this way. We could do it this way. It would just be slightly different. It would be, I'll leave this here so you know. It would actually be BOH.
Yeah, that's right.
And then OH minus and B plus.
Yeah.
So this
I
one's
know
a good
that
one.
now.
Yeah,
Yeah.
100%. This one is, we'll label it as funny ha.
Okay, thank you.
By adding a basic solution to the methyl orange indicator, such as NOH, the concentration of HB will change this. I know what you mean.
Oh, yeah,
BOH
BOH. Yeah.
would increase drastically due to the reduction of NaOH. Introduction, yes, sure. As LCP states, the forward reaction would then be favored in order to reach equilibrium.
That's wrong. Due to LCP, the forward reaction. Yeah, I read that wrong.
No, it's okay. I wouldn't say due to, I'd say as. This is fine. Okay. As LCP states, the forward reaction would then be favored in order to reach equilibrium. Now, one thing I would do is actually define LCP. So with any LCP question, there's usually one mark actually attached to just defining it. To defining LCP, it's almost always a mark. So anytime you use LCP, just slap a definition in there. It takes you 10 seconds. And it's going to save you marks. I guarantee it. So something you can take is just from up here. This is what I wrote.
Yeah,
So
that makes sense.
I'll copy this one in to exactly where you had it, just here. That's how I would structure it then. You define the LCP. As a result, a larger amount of B minus. Yeah. Larger amount of B plus will be produced, resulting in a yellow color for the solution, indicating the solution is more basic. Okay. Now, the only thing that makes this response a bit harder to follow is that the system we've been given in the question is in terms of it's in terms of an acid dissociating into its two parts, right? Did you get that bit where we were relating which of these is HA and which of these is A minus? I'll scroll over.
Yeah.
Yeah. So which of these is HA, which of these is H minus?
HA is the bottom one because it has a hydrogen.
Correct. And the top would be this A minus, and the H plus is a bit confusing here. It should be off to like the side of the plus, H plus. But when we're given something in the question, oftentimes they're going to want us to talk about it. And what's actually happening in this system is important here. So this is good. However, we haven't referenced exactly what's from the question. And it's this system that they want us to talk about. So we can actually talk about it through this same equation. If we were to do it. Taking that same indicator equation, talking about it through this. Because this is representing the indicator, right? So if we add NaOH to this system, what happens? Benji?
You create more blue.
You would create more blue.
Yeah.
And how does that happen? NaOH, what does it dissociate into?
Na plus OH minus.
Yes. What in these constituents are actually reacting? Is it the Na plus or the OH minus?
Oh, the OH minus.
Yeah, it's the OH minus. The OH minus goes and does what? What type of reaction?
Don't know.
With this OH minus, what does it react with in these parts? Same one.
Yeah. Oh, because it forms a hydro.
Yeah,
Oh,
it's going to
that's
be
right.
a
Yeah.
neutralization, and we go bang to H2O. So these are the equations I would be writing down in this scenario, because we're talking about we're talking about the indicator, the reaction that's happening when you're proposing you add NaOH, and then the dissociation of NaOH, and then what reaction actually happens with the parts of NaOH, the OH minus in particular, goes and does a neutralization. Does that make sense?
Yeah.
Yeah. So then how does that affect the equilibrium? We've got neutralization, which has consumed these parts. How does that affect this?
Well, would you have? You'd have less H plus.
Correct.
So the equilibrium, LCP, it'd favor the forward reaction to reintroduce the H plus, and then
Yep.
you get your more basic color of yellow.
Uh-huh. Yeah. Does that make sense? Miriam, make sense?
Yeah.
Same kind of thing, right? It's just the opposite way. So this is the point. We're probably in awareness stage right now for this content. We've got probably understanding for LCP and collision theory, but then exam readiness is a whole other thing, because you'll get these questions and it's like, oh, I don't really know what they're looking for. And you can't know. That's the truth. You can't know unless you've done it before. And the more you do them, the better you'll get. Fair enough? Okay, let's move. That's all for indicators. Any final questions before we move off it? Great. Acid-base reactions, 3 very important ones. Acids and bases, acids and carbonates, acids and metals. The general forms, you should know from year 11, potentially. What would you get when you react an acid and a base together? What are the two? Salt and water. What would you get when you react an acid with a carbonate?
Salt water, carbon dioxide.
Salt, water, carbon dioxide. So carbonate, think carbon dioxide.
Yeah.
And then finally, salt and metal. Sorry, acid and metal. Acid and metal.
Is it?
Acid and metal is salt. Is it salt and hydrogen?
Hydrogen, gas. Yes. So that's the last case. There's only 3 cases really.
Salt, water, hydrogen, or just water, hydrogen?
For the acid and metal,
Hmm.
just salt and hydrogen.
Salt and
Gas,
hydrogen.
no water.
Okay.
No water, because there's no oxygen in the left-hand side.
Yeah, okay.
Yeah, does that make sense?
Yeah.
Good question. So those are the 3. And these will allow you to figure out most of the reactions in this whole module. Are you guys fine with valencies and crisscross method and all that kind of stuff? With being able to figure out what you get from a reaction?
What is the crisscross method?
Yeah.
Like, as in, if you have sulfate 2- and you have hydrogen plus.
Crisscross the ions?
Yeah, you crisscross their valencies.
So H2SO. Oh yeah, okay, yeah, I guess I know that.
Yeah, you can, I don't know, like some people learn it that way, but as long as you know how to figure them out, then you'll be okay. Whatever way it is you have. With the valencies, if you can remember, you swap them around. That's all it is. Yeah? Any
Mostly.
questions? Yeah. Any questions on these? So there's some questions here you can practice. These 5 cover basically all the cases you can get. Have a go of these in your own time this next week and check them online with literature. Okay. This one's the fun one. I like this. Applications. So applications. Chemistry is all in the world around you, and you just haven't yet seen it fully. Again, the dot point reads, investigate applications of neutralization reactions in everyday life and industrial processes. Yeah, exactly as it says. You just need to know a few ways neutralization can be used at home, a few ways neutralization is used in industry. The point of this section is not for you to memorize all of these case studies. That is not the point, and I cannot emphasize that enough. The point is that you understand each of these case studies and the chemistry behind them, so that in your exam, when you get presented with a new application, it's actually pretty much just the same, but in a new context. What you do need to do is memorize at least one everyday and one industrial case. That is at least what you should do, as in the reactions behind it and how it works. That's the minimum. If it was me, I would have one everyday base, one everyday acid, and one everyday and one industrial acid and base. But you'll see in the moment for industrial, there's one that covers both of them. So you don't really need 2 for industrial. So it's 3, I would say, is what I would go for. Okay, does that make sense? First of all?
What you meant memorize a new one each day.
No.
Oh,
No.
that's a lot.
Not
No.
every day. 1, 3 for the whole term, your whole year.
Okay.
Not one every day. I'm not asking you to resign yourself to a life of chemistry. So everyday applications. I've got 3 of them on this doc, by no means exhaustive, but these are some of the most common, and they do come up in exams. Case study 1, antacid tablets. So when have either of you had heartburn before, where you get like, no, basically what heartburn is, or acid reflux, is when you get stomach acid coming up through your esophagus and it burns in your throat. It's quite an unpleasant experience. So people get the stomach acid, which is hydrochloric acid, coming up through their throat, and it's painful. So what we have, and I don't know if you've seen stuff like Gaviscon ads on TV for reflux, but there's medications we have that can reduce how painful that experience is. And the way they work is through neutralization. What these antacid tablets contain, they contain stuff that neutralizes acids, which would be what? What do you reckon?
Bases.
Bases. Basically, they contain a combination of all sorts of bases. And some of the more common ones are magnesium hydroxide and aluminium hydroxide. There's many other there's carbonate and acids, plenty available. All it is you need to know is in an antacid is base. You swallow it in your stomach. In your stomach, you have a neutralization reaction, which raises the pH of your stomach acid, so it's not as acidic. And we haven't covered pH yet, but a low pH, so pH 1 is more acidic than pH 2, then is 3, and so on and so forth. What is important is you need to have a specific example. For example, magnesium hydroxide, for the one you remember, magnesium hydroxide, aluminium hydroxide, and you should be able to write out the equation that happens when that neutralizes with stomach acid. That's what you're looking for. The reason why it exists, so acid reflux, how it works, and what is working, so the examples. That's the 2 things really for each one. Does that make sense so far?
So you only need one of the equations?
I would just take one, yeah.
Okay, yeah.
Okay, let me know when you're ready to move on to the next one. All good?
Yeah.
Okay, case study numero 2. preventing tooth decay. So in our mouth, there tend to be acids that can cause oral cavities and cause our teeth harm. So what do we use? We use a base again to neutralize. So toothpaste is actually weakly alkaline. It helps us neutralize the bases in our mouth. And it has certain components, calcium carbonate, aluminium oxide, magnesium carbonate, that can help neutralize these bases. My theory, I actually don't know if this is true, but my theory is that you know how toothpastes froth up when you use them for a while, you brush your teeth and they're quite frothy. My theory is that there is some carbonate in your toothpaste which reacts with the acid on your teeth and produces carbon dioxide gas, which is held in the froth and it gases up your toothpaste. I'm not sure if that's true, but that's just me thinking. And that's the kind of thinking I want to encourage you guys to really think about. Like, why are things happening in real life? Because that'll make things make a bit more sense. Is that okay? This last one, I know for sure is true. And I hope if you guys have done some baking over your time, you may resonate with this one. So baking soda. Baking soda is the last case. NaHCO3 is the formula. And it's like the white powdery stuff you put into cakes. Have you done some baking over your time, Benji?
Yes, I am.
Yeah?
Yeah.
Familiar with the substance?
Yes.
Good. So when you put this into your cake, what happens?
Rises.
It rises. If you don't put baking soda in your cake, what kind of cake do you get?
A horrible cake.
Like an abysmal cake. It's going to taste terrible, flat, terrible cake. So what has happened with the baking soda? Does anyone know the chemistry? There's an equation to help. What has happened?
It's that equation.
What do the X's stand for in that?
X is general, so it means anything. So it could be, well, here it'd be an acid,
right?
It'd be it'd be like HA, but it's the A in that H. Okay, so what's happened here? We have our bicarbonate solid. It's reacted with some sort of acid. And it's formed these products. A salt of sorts, water, and carbon dioxide.
Okay.
So when we put bicarbonate in our cake, what's happening is this reaction here as we bake and as we let it rise. It is carbon dioxide being released in little pockets as the cake is sitting there, and it's expanding outwards because of this carbon dioxide, which is now filling up this space. And in a cake with bicarbonate in it, you're going to have a very fluffy, bubbly cake because there's all these little pockets of gas, and that's the CO2 from your baking soda. So when you make a cake, next time, you look at the pockets and you're like, that was once filled with CO2, and I know that now. So that's the application, which for most people is most relevant at this age anyway. I don't think most people have reflux at this age. But those are examples of everyday applications. Does that make sense? So when you start thinking a bit more widely about things in everyday life that might be chemically related, you're not going to get everything straight away. But as long as you start thinking about things and wondering, that's when you'll make some cool discoveries along the way. Okay, they're the everyday ones. We're going to move on to industrial in a second. Give me a thumbs up when you're ready, Benji. All right, industrial applications. I only got 2 of them. You only really need to remember the first one, and it covers all bases. Acids are corrosive and bases are caustic. So if you have, sorry, I should introduce this. If you have a spill of acids and bases in an industrial setting, so large scale spill, we're talking thousands of liters, you're going to need to clean it up, because if anyone touches that or inhales the fumes, you're going to be in big trouble. So you got a big spill of acid or base. You actually don't know what the acid or base is. You're going to have to get rid of it somehow. And the best way is, again, through neutralization to bring it back to a pH that is not dangerous anymore. When you have this spill, you need to consider, first of all, is this an acid or a base? Do we know? If we know, that'll help us because we can choose a more suitable thing to neutralize it with. How big is the spill? Is it, big, small? How much do we need to neutralize? And is it actually dangerous? And lastly, how strong or concentrated is our acid or base? Because they're different things. Strength and concentration are different things. We're going to cover that in due course. Let's not go into it now. There's a number of things that would help us for our neutralizing agent. We'd obviously want it to be cheap, safe, and storable so we can use it whenever and doesn't cost us an entire bank account. We'd ideally want it to be weakly acidic or basic. So if we go and add too much, we don't instead create a new hazard. And lastly, we also would want it ideally to be solid because that way we can just kind of sprinkle it across instead of making a spill that spreads outwards if we add a liquid to try and neutralize. So those three things are helpful. But there's one thing above all that is so helpful. If we add what we call an amphiprotic substance, Benji, you've got a bit of a head start here, so you might know what that means. What's an amphiprotic substance, you reckon?
Amphiprotic is whether it can both donate and accept a proton.
Yeah.
No? Yeah.
So what that means, Miriam, is that an amphiprotic substance can act as both an acid and a base, which is crazy to think about. But things can act as both acids and bases at the same time, depending on what situation it's put in. Just gonna let that marinate for a second because it's a bit whack. Bicarbonate is one of those substances.
Yeah, it is.
Yeah, bicarbonate. So I'm gonna put this in your doc. An amphiprotic substance, because this is really cool to me and also very relevant, not just cool. Amphiprotic substance is a substance which can act as both an acid and a base, and it's underneath a theory, the Bronsted-Lowry theory, that you'll learn about soon.
Isn't that with the auto ionization of the water? With that thing?
Yeah, but that's a little bit different to the amphiprotic stuff. That is also related there, though. So yes. Substance that can act as both an acid and a base, that's perfectly fine for now. And one of these substances is HCO3 minus AQ. Why is it amphiprotic? What happens if you add hydrogen to this HCO3? What happens if you add a hydrogen to it?
Turns into H2CO3.
Yeah. H2CO3. I should make this double-ended. And the double-ended arrows will make sense soon. I'm just not explaining why yet. There's a method to the madness. What happens if you add instead? Pardon?
I just realized why the reverse arrows are there.
Yeah.
Yeah.
So then, Miriam, what happens if you add an OH, do you think, instead? An OH minus to
H2CO4.
H2, not quite. Think about what happens to this. If I'm just going to tell you now, this is an acid. What happens to this?
Oh, it gets neutralized. So H2O CO3.
Beautiful. CO3 2 minus. And I'm very lazy with superscripts and subscripts. It's way too hard on Word. So I'll just keep it like this, if that's okay with you guys. So we have two possible neutralizations possible with bicarbonate, both with acid and base. And that's what makes it such a great agent to neutralize spills with, because it doesn't matter if it's a base or acid, you can use it anyway. And it's also weak. So it's not going to go too far. And it's also solid. So you can sprinkle it over. So it's a great option. And that's why I love this case. This is a very, very good one. I recommend you learn this one, because it covers both the acid and the base. Then the other one, I'll give you a moment. Okay, the other one is treatment of wastewater in the in specifically the semiconductor industry. I don't even know what that is. You have HF, which is constantly put into wastewater. So what do you name this acid if it's HF?
Hydrofluoric.
Hydrofluoric, agree, Miriam?
Yeah.
So if it's an anion with H, hydrofluoric acid. Same as HCl. And the Miriam, what would be HBr?
Hydrobromic.
Yeah, there you go. Figured it out without having to memorize it. So if you have the rules, it helps, but also memorizing just makes things easier. So it's just like that going forward. Okay. In this wastewater, you have HF. It reacts with, and you can neutralize the HF rather with a base. So sodium hydroxide or calcium hydroxide can be used to neutralize that acid to create just CaF2 and 2H2O. CaF2, you'll notice, is also solid. So have you guys spent some time memorizing your solubility rules by any chance?
My brain doesn't like them.
Yeah.
I'll get there,
Isn't
but
it like Snape or something? I forgot what it was.
There's many an acronym, but
Yeah.
you just need to find a way that,
something.
yeah, there's my ones were so broken back in the day. I had the worst acronyms, but there's better ones out there. I think I hear PMS Bear, NAG SAG.
PMS, Castro Bear,
Yes.
something.
Yes. If those work, use those. But if you're lazy for now, and this is not a long-term solution, you need to remember them. But if you go to your formula sheet, let's go. You go to your formula sheet, see a bunch of these on the front, solubility constants, right? If you ever forget your rules and you're just lost, this entire list is pretty much all of the insoluble things that you can get in HSC. So if you're ever lost, there's a few exceptions of things that are slightly soluble here, but for the most part, all of the things here with a KSP and it's with a power of like bigger than negative or smaller rather than -6 is pretty certainly insoluble. So anything with like -7 and below is going to be insoluble. The ones that are exceptions, you'd have to go and remember them, unfortunately. All you need to do is spend some time on the solubility rules, get your head around those. So same kind of method as before, which we use to memorize the names of the acids and bases or the acids. Just test yourself, cover check, be active with it, and you'll find you'll learn a lot quicker. Spend like 5 minutes a morning for the rest of the holidays, something like that. Okay, so that's the wastewater case. Not a whole lot interesting here, apart from the fact that the calcium fluoride that you make is solid, and it makes it easy to separate out after you've done this neutralization. That's all. But I would rock with this one. This one's nice. Okay. So again, I like to show you the questions you're going to get. Something like this is very common. What's becoming increasingly common is they give you an application, you have to explain it. So they'll give you the equation, you have to explain it in your own words. Or they'll give you the situation. But the question that I always saw back in my day, and I still do see, is to explain how acids and bases are used in one everyday and one industrial situation. So essentially, you just need to have one memorized for each. Fair enough?
Yep.
Okay. Any questions at all, please ask.
Wait, what is the everyday life application that uses an acid?
That uses an acid. Fair, there isn't one here.
Yeah, because they're all bases, aren't they? Yeah.
That's a good point. I should get one with an acid. What would be one with an acid? Vinegar as a way of cleaning, like vinegar and lemon juice as a way of cleaning soap scum. Because soap scum is going to be your base, and you can use your vinegar and citric acid from lemon juice as a way of neutralizing that base and removing soap scum. Not soap scum. No, it is soap scum. Yeah. That would be one. Does that make sense?
Kinda.
Huh?
Not
Kind of.
really.
Let's get an equation. Let's get an equation. Record. Wait, this is not what I wanted.
Oops. Because I know that when I went over this, there wasn't any acid base ones either.
Yeah, it's a good question. Because I remember having this problem last year as well, and now you're reminding me of it as well. So that's good. How about I will send you guys a message when I have a case study in the chat, and you guys can reference that one.
Yeah, okay.
Okay. And I'll be updating these notes as well, because I've basically just gone and rewritten all my notes from last year
Right.
to try and make them better, but obviously I've missed this. So very good pickup. Thank you. Okay. Last thing for today. And I promise, I know it's been a lot. I don't know if we want to rush through this, to be honest, but we started a little bit late. So you guys going okay with going a little bit over time?
Yeah, that's fine.
Neutralization enthalpy. This is something you did in year 11. Something you did in year 11. So when you react an acid and a base, do you guys remember if this is an exo or endothermic reaction?
Mixing a what?
Pardon?
Mixing an acid and base.
Yeah. Is it releasing heat or is it taking in heat? Have a stab.
I don't remember.
Got a 50-50. Miriam,
I think
have a
it
go.
was releasing.
Agree, Benji?
I don't know.
Have a stab
Oh.
as well.
Yeah, sure. No, I'll say endothermic.
Good.
So
You
one
should
of
have
us
backed
is
her.
right.
She was correct. So
Yeah.
exothermic releases heat. Neutralization. So think of it this way. Neutralization is going to release heat. The temperature of the solution is going to increase, right? So when you add together two solutions of acid and base, you're going to get an increase in the temperature overall, right? Because it's exothermic releasing heat. The whole point of this dot point, conduct a practical investigation to measure the enthalpy of neutralization. You're essentially trying to figure out how much heat is released for each mole, or for each, how much heat is released for each mole of acid I react with base. That's what you're trying to figure out in this prac. And there's a prac that you may have done back in the day where you would take an initial temperature of a solution, perform a reaction, and measure the end temperature. And you get a change in temperature. Is that familiar at all? It's okay if it's not.
It's very kind of vague. Could have been.
Yeah, it could have been many different experiments. Could have just been boiling water, in fact.
Yeah.
But that's essentially what happens here. I'll run through the procedure quickly. All you're doing is in what we call a calorimeter, which I'll get a picture of. In a calorimeter, which is some sort of container that is insulated from the outside in, usually a styrofoam cup. It actually does quite well as an insulator. You put inside that calorimeter your solution. So it might be your acid or base, one of them first. I'm going to leave this over here. So you'll put your acid or your base inside after you've measured out an equal amount of them. So 50 mils of 1 mole HCl, 50 mils of 1 mole NaOH. You have those sitting in two little beakers off to the side. Following so far?
Yep.
What you're going to do, don't worry so much about the stirring, but it is important. What you're going to do first is place let's say, your HCl into this empty styrofoam cup to start. This is meant to be empty.
Yeah.
Let's say now we've filled it up with some HCl. We measure the temperature of that HCl to start. Then we're going to add all the NaOH in. So what reaction is going to happen?
Neutralization.
And the equation is
Salt, water, carbon dioxide.
not quite
No,
carbon
wait.
dioxide. When do we carbon dioxide?
H.
Carbonate.
Yes.
Wait, yeah.
Get it when there's carbonate. There's no carbonate here though. So what's going to form here? Acid and a base.
Salt and water.
Salt and water. Good. So we've got salt and water from this reaction. And it's neutralization. That's the important part. You're going to record the temperature over 3 minutes. How's the temperature going to change over this 3 minutes, you think?
Gonna go.
It's going to go up.
Yeah.
It's going to keep rising. Straight line. And then stop. And stay at the same temperature. What kind of shape is this curve going to make? It's going to go up. Does it keep increasing faster? Does it tail off? Or does it go linear?
Oh, it'd be a parabola because
Uh-huh.
because at the beginning there's so much concentration, it's gonna all react really quickly,
Mhm.
and then the slower there'll be less concentration because it's turning into heat, and then it's just gonna slow off because of collision theory.
Yes, so we've got the right idea. And there's also something else happening, something we like to call heat loss. So your curve is going to look like this. It's going to tail off. I'll make it a bit quicker. It'll probably be something like this. You go up very quickly at the start because you have lots of collisions between plentiful acid and base. You're going to hit a maximum point somewhere before you start to drop temperature. Why are you dropping temperature?
Heat loss.
Heat loss.
Being
Because
absorbed by the
yeah,
surface.
your calorimeter is a good insulator, but it's not perfect. There's no ideal insulator, really, that we have available in our school labs. So we're going to hit our solution to say from 22 degrees room temperature, or 25 degrees room temperature, say, it goes up to maybe 28. And then it's going to start coming down slowly as we lose heat. Are we going to actually reach the theoretical peak temperature? Are we going to reach that? Is this theory? No, it's not. Why?
Because you're having heat loss all the way
Yeah.
through.
Exactly. And that's another reason why it slows off, because not only are you having less reactants present, you're also having heat loss at the same time. So you hit a maximum and you start dropping off, bang, down here, until you're eventually back at thermal equilibrium with the room. Does that make sense? Okay, so then my next question to you is, do we take our measurement for the final temperature from where we stop recording, or do we take it from somewhere else? So we stop recording here, say, after 3 minutes, and our curve looks a bit like this. Where do we take our final temperature from?
Is it our peak temperature, our highest?
It's actually at the peak. Why does this make more sense than this end temperature?
Because you're trying to calculate the total change in heat,
Uh-huh.
because you need that. So
Yes.
the like change that you like get the most out of is from your bottom to your peak.
Exactly. So if you were to take this end temperature, this makes no sense anymore because you've seen yourself get more heat released at this point compared to here. If you were to take this end temperature, this is showing that like this is your total amount of energy. When you know you've actually released more to get to this top temperature up here. So you just take the top one. Take the highest possible temperature from this curve instead of the end. Okay. And then finally, once you've gotten that change in temperature, that allows you to do all the calculations. And the calculations. Let's skip over this for a second. 2 equations to answer all your questions, basically. There's some like peripheral ones, like C1 V1 equals C2 V2. But these ones are the meat of it. If you know these two, you're going to be able to answer pretty much everything. Let me get rid of this line. Q equals MC delta T, and delta H equals negative Q on N. These are both on your formula sheet. but you need to be familiar with what each of them actually refers to inside the system. This is the last thing we'll talk about, so stay switched on for this little last bit, and I promise you'll be able to rest your brain after this. Okay, let's get into these. Q equals MC delta T. What do each of these parts mean? Does anyone remember from back in the day? I'll scroll up. We can't. Sheet. Q equals MC delta T.
Your C is your heat capacity of water. Well, we're using water in this one, so that's heat capacity.
Okay, and then we'll swap. We'll do one each. So C is heat capacity of water. What does that mean first, Benji? What does heat capacity of water actually mean?
Isn't it? It's the amount of energy you need to raise the temperature. So like, it's the amount of energy you need to raise the temperature of water in this case. I'm pretty sure.
Yeah, pretty much. It's a measure of how easy it is to heat something up. That's how I describe it.
Okay.
If you have a very big heat capacity, so say you have like 1,000,000 heat capacity, it means you need 1,000,000 joules of energy to increase 1 kilo of water by 1 Kelvin.
Yeah.
So if your heat capacity is 1,000,000, does that mean it's easy or hard to heat your solution? Very hard. So with something with a smaller heat capacity as a comparison, that means it's easier to heat. So heat capacity tells us how easy it is to heat a solution. And the units are joules per kilogram per Kelvin. I've made a little typo here, which I'm gonna have to fix. Actually, that's why I underlined it. Okay, because I need to fix this. This is a typo. The units are meant to be flipped, but yes, that's what heat capacity is. Does that make sense, Miriam? Any questions? Okay. Your turn next. What are any of the other three things? Q, M, or delta T?
Delta T was the change in temperature,
Of what?
the solution.
Solution, so the water.
Mm.
Okay, swap it around. Benji, Q and M, what are they? What's one of them?
M is the amount of water you have.
Yes, the amount of water. And usually in these situations, when you're combining solutions, you're gonna not actually have mass. What are you gonna have instead?
Volume.
Volume. How do you convert between volume and mass for water?
That's a 1-to-1, no? Oh, it's like a milliliter is equal to a gram.
Yes, good. Does that also ring true for you, Miriam?
Mhm.
Okay, lastly, Q. What is Q?
Q. Forget Q. The others I'm fine with.
That's okay. Q is
It's heat something.
no, that's it. Just heat.
Just
Q is
heat. Okay.
total amount of heat you released. Did you release 5 joules, 500 kilojoules? What amount of heat total? And they're the 4 parts. If you understand what the 4 parts actually are, then you can use this equation well. A lot of people go into exams not really knowing what the bits are of each equation. The only difficult thing with mass in this situation is that in this prac, you're going to be combining 2 solutions together. So how does that affect your mass of water? So for example, here, we had 50 mils and 50 mils of NaOH and HCl. How much mass of water did we actually heat?
100 grams.
Why is it 100 grams?
Oh, wait.
No, why?
Wait, is it? I can't
Miriam,
remember
why?
this
What do you
actually.
think? How
50
much water did we heat? 50 plus 50 makes 100, and it makes sense. So if we're combining 2 solutions together and we're doing a neutralization in the combined solutions, we're heating the combined mass. So you need a factor for that. That's why the mass is there. So if you're heating more, obviously you're going to need more heat to get the same temperature change out of it. Does that all make sense?
Yeah.
Good. And finally, delta H is equal to negative Q on N. This is the last one, and this one's a bit easier. So delta H is change in enthalpy. Can anyone define what change in enthalpy actually is? What is change in enthalpy?
The amount of heat gained or lost.
Yes. And is it a total amount or is it like a rate?
Enthalpy is like per mole. So like
Yeah.
it's the amount of energy change per mole.
Yes. So combining that together, Enthalpy change is the amount of heat gained or lost per mole of reaction that happens. So
Okay.
to add a little bit onto that, because the amount of energy gained or lost would just be heat. That'd be Q. But the amount of energy gained or lost per mole of reaction, that is then change in enthalpy. And we can think of the word enthalpy as just heat. Just think of enthalpy as heat, your life becomes easier. Okay. Q, again, total heat, it's the same Q up here. So you can very easily substitute between these equations using Q. You cannot, however, substitute using N and M. These are different. M in Q equals M cap is mass of water. N in the second equation is moles of reactant, which is not water. This is your acid and base. So the moles of reaction that happened is N. And that's pretty much it for these equations. The last important thing for any calculation question, and this hopefully might solve some of your problems with calcs, Miriam. Units. I know that it's such a pain to write units behind every number, but as you're practicing, I cannot emphasize how helpful this will be in the long run. So when you're doing calculations, this applies to you too, Benji. So don't treat this as nothing, because this is very important. When you're doing calculations, you need to write, as you're doing your calculations, units behind everything until you can actually do it second nature. Do not shortcut this. Reason being is if you don't match your units, you're going to be out by a factor of 1,000 or up below or above, because you're doing joules and kilojoules or kilograms and grams and different things. So what I mean by matching units, to be clear, for example, if you get a question like, let's do the one, we're not going to do it, but there's some down here. Let's not do the questions. I'll give you these examples here. So say you're getting asked to calculate, no, we'll use this. You're getting asked to calculate Q from all of these numbers which have been provided to you or you've already found. M, C, and delta T you've already found. By matching units, I mean, if your C value is in terms of joules per kilogram per Kelvin, everything else in your equation will be in terms of joules and kilograms and Kelvin. You must make it that way. So if we're substituting M and delta T to find Q, what unit would our M value need to be in if we're using this one over to the right?
Kilograms.
Kilograms. Our delta T is going to be Kelvin, degrees Celsius. Actually doesn't matter for delta T.
Yeah.
It's better to keep it in Kelvin anyway. So we'd put it in Kelvin. And Miriam, what unit would you get out for Q?
Joules.
Joules. Match your units. You will never make factor of 1,000 mistakes again. That being said, you should very easily be able to pick up these unit mistakes, because when you're finding that this neutralization you did in a beaker released 5,000 kilojoules of energy, you're going to raise your eyebrows and be like, no, that's not right. So use some sense to it, but also for now, just keep your units in there as you go for all your calcs. There's 2 practice calcs at the bottom, one from Conquer HSC, very good website online. Use this resource, very helpful. It's free, all notes there, questions, it's very good. And there's also a question from the Knox paper in 2023. Solutions below, give them a crack before next session. There's a few things for you guys to do from here, which hopefully will actually help you more than waste your time. They're very relevant to what you learned, so you should be able to do them. If you get to question 18, get through those questions and comb through them. You should have a pretty good understanding of what we've done today. But that's it. Next time we'll be covering acid-base theory and going a bit further with that. Any final questions before we wrap up today?
One unrelated question.
Yep.
Are we weekly or bi-weekly?
We are weekly. We are weekly for the next 4 weeks.
Awesome.
Next
Thanks.
4 weeks. All right. Benji, you right?
Yeah, I'm good.
Any questions?
Nah, I'm good. I'm good.
Okay. How did you guys find it overall? Was the pace quick for you guys? Was it digestible? Because I can change as you guys want. How would you find it?
That was good.
I liked it. It wasn't going too slow, definitely not too fast.
Okay. Anything that you guys would prefer from me? Because I can change as well. I'm not here to just yap at you guys. Anything else you want?
I know.
This
I
is
think
good.
it's- yeah, it's
Yeah.
good.
Good? Helpful?
Yep.
Okay. Tell me one thing you learnt today, and we'll wrap it up. Miriam first. One thing you learnt.
So, well, the HA is for acid.
Yep.
In this, yeah. Oh.
Oh.
Oh no. Okay.
I think he froze.
Is he?
Yeah, he's dead.
Okay. I thought he was just standing really still.
He'll come back at some point, hopefully.
Okay. My laptop's about to die. Just about last.
Next lesson's gonna be death, and I know it as well.
Pardon?
The next lesson's gonna be horrible because I've done it.
Oh, there he is.
Yeah.
Okay. Sorry. My phone died because I'm on a hotspot. And I didn't realize it was dead because I just moved apartments and I don't have Wi-Fi yet.
That's
But
fantastic.
what was the fun fact you learned today, Benji?
Oh, in the cabbage experiment, you can't go
Yeah.
above 120 degrees Celsius.
Yes, so important because when you're going to do a cabbage experiment in your real life, you should never go above 120 degrees.
I will always do a cabbage experiment in real life.
Right. That's all for today. 15 minutes over time, so sorry about taking a bit more of your time, but I'll see you guys next week. There'll be a third person here. He just couldn't make this session. He was on a Friday one for this week.
Cool.
Thank you so much.
Done with that.
Thank you. That was
And
awesome.
all the best.
You too. Have a good day.
Nice week.
Yeah.
Bye.
Bye.